By now, I think all of you know who Kristian is, so I'm not going to say much and let him do his thing.
All right.
Welcome.
Okay, so to be on the safe side, I'm Kristian Larsson. I work for Deutsche Telekom within a project called TeraStream. It's I'll inform you what that is. So today I'd like to show some of the things that we have been working on lately in regards to testing. We're doing some fascinating things, I think, on the testing of network provisioning as well as BGP route policies. Here's the agenda for today. I'll start out with a quick introduction of TeraStream and RTNSM. We'll continue very briefly, talk a little bit about containers, then jump into the more interesting things, which is actually testing network provisioning. I'll talk about something called VRNet Lab. It's a tool that we're using. Continue with service-aligned monitoring, and finish off showing what we're doing with regards to CI testing for BGP route policies. Like I said before, Carl was here. I think he gave me a kind of an excellent introduction on the whole netconf yang space. We're using that a lot, so thank you, Carl. Also, I won't be talking that much about why we're doing network automation. I hope this is clear for everyone. This is the future. Okay, so TeraStream. TeraStream is the next generation design kind of a fixed network for Deutsche Telekom. It looks something like this. Generally speaking, it's just a simplification of a network. In particular, if you think about the kind of infrastructure that's currently rolled out by Deutsche Telekom in Germany. So we have a couple of, we call them R1s. This is kind of edge routers, provider edge, whatever you want to call them. So these connect your customers. You have around 5,000 customers per R1. This is IPv6 only access. You get 5,000 R1s roughly in a region such as Germany. And then we have these R2s up here. That's what we call the kind of collapsed core peering and data center box. They're connected together using this really basic kind of optical technology. We're using coherent 100 gig DWDM. IPv4, since this is an IPv6 only network, IPv4 is realized as a service. So we're kind of tunneling that just on top. But most importantly, for my talk here today, is that all of these things, the components that we have in TeraStream, we want them to be provisioned fully automatically. Enter RTNSM. This is the real-time network and service management system, I think it's called. And this is kind of the management brain of TeraStream. We aim to build something that is fully automatic, for some definition of those words. It's not Skynet, so it won't figure out by itself where to build a network. But the idea is to completely automate most of the day-to-day tasks that you have in network operations. For the remaining bits, we as humans should interface with a high-level, kind of abstract API of this system rather than going down to the devices. So no humans allowed, no humans making a mess with the router configuration, right? Having this system and, doing most of it just fully automatically, but the remaining kind of human interactions through all these APIs enables us to do testing of everything. We guarantee consistency and enable this testing. So the RT in the name is for real time, but most of the time it's actually not. Some people talk about SDN, blah, blah, blah. I'm not sure if this is it, but we don't get involved in real-time things like detecting failures and then trying to route around that. That's still delegated to the network. We're letting the good old routing protocols and so forth do that. Here's the overarching architecture of RTNSM. So we set out to solve a pretty big problem here. I think or many problems. And as with any sufficiently large problem, this one can be solved by a stack of pancakes. Obviously, this is a representation of the abstraction layers that we use to kind of divide and conquer this problem into many much smaller and more manageable problems. The bottom layer of the pancake is the one that we will focus on here today. I guess that's the one that kind of represents the provisioning part, is talking southbound down to devices, netconf yang, obviously, and on top it exposes a API, also yang modeled, to the higher layer pancakes or systems. An example of one of the higher layer pancakes or systems would be the capacity planning component. So capacity planning system would think, I need to add more capacity between router A and router B. It doesn't care about all the details of how to do this. I mean, you need to figure out IP addresses, IGP metrics, things like that, right? But the capacity planning doesn't care. It only wants more capacity between these routers, which is why we're doing the whole abstraction, right? I tried to show kind of an example here. So at the very high level, we have an intent. This is the capacity planning system thinking, oh, I want 100 gig capacity between A and B. As we kind of move down the layers, we will enrich this with the details that we need, such as the interfaces. We'll talk to some inventory system or whatever. We have an optical control plane component that figures out which DWDM wavelengths should we use to connect these two routers, which is the optimal one, what's the output power that we should use, and so forth. We have IGP metric, IP prefixes, things like this, right? So we enrich this high-level intent with more information, and we end up at the bottom where we have enough to render our configuration. It's netconf yang. Also written tailf NCS or Cisco NSO. So this is what we're actually using. The bottom layer in our stack is based on their product. And there's an example of how to configure a DWDM interface on a XR router. I'll try not to talk too much about NCS today, but I guess it's a little bit inevitable. I'll also try not to talk too much about containers, but I do want to mention it. It's one of the technologies that we use. It's great. Operationally, it's a joy to work with, but the primary reason that I'm mentioning it here is due to the way how it kind of integrates with our CI system and about something called immutability. So immutable means it's fancy programming lingo for something that can't change. So the nice thing about containers here is that we compile our code once, we build this Docker image out of it. Now I said Docker, not container. We build a container image out of it. We run our CI tests on this thing, and then we deploy this image into production environments. Since we know that the container image is immutable, we can trust the system to run the same code that we have tested in our CI system. It will also run the same thing in the production environments. So this is a great tool. Last on this slide is something I picked up on, I think it was Twitter a while ago. A container is a function call. And for those not super familiar with the whole container concept, I think this is a great way of looking at it. That really resonated with me. Some think of it as a kind of a minimal virtual machine thing. It's really not. I like it more as think of it as a function in a programming language, and I like to think of it like that. So we're using containers to easily deploy NCS, and make sure that we have in production is also what we tested in CI. So with the scene set, let's get to the more interesting bits, namely testing of network provisioning. Most modern provisioning systems look about the same. You have some form of input data, you have logic, often in a programming language, and then you, from that, you may calculate things, do lookups, do whatever. You collect this as a bunch of variables, you feed that into some form of templating language, and out comes a configuration. If you look at Ansible, it does roughly the same thing. You have Jinja 2 as a templating language. The case of NCS is roughly the same thing as well. So what we get here at the end, the config, is just text. All of the pieces here is just text, really, right? Input data is text, logic programming language is text, templates are text, and the config is also text. So conceptually, it's very simple to write tests to make sure that we output the correct text here at the end. But in practice, it often means that you'll more or less copy kind of your template and then say, this is the expected output that you want from your system. If you make a small error in the template, that'll probably propagate to the expected output as well. As I mentioned before, most of the stuff we're doing is netconf. That means that the output is XML, because XML is what netconf uses to encode things on the wire. So what we can do more here, and just not look at this as text, we can actually do XML validation, if that's what we want. Also, since all the interfaces here are Yang modeled, we can actually look at the output and see if it conforms to the Yang model that we have. And there is, in fact, something. It's called NCS. It's NetSim. It's part of the NCS package. This is what Carl used before to simulate virtual routers. So what this does is you load up a bunch of Yang models into it, and it will kind of simulate so that you get what looks like the northbound API on a device. If it's an XR device, right, you talk to it with netconf, you ask, what models do you support? And this would look just like it. So with NetSim, you get something that looks like ISXR or looks like Juniper, and you can put ISXR config on it, or Juniper config, but it's just a simulation of this, right? So you will never be able, you will get your syntax check, you will get semantic checks, and again, this is what Carl was talking about, only a very small niche kind of configuration makes actual sense, right? A lot of those things will actually go undetected by this. If you configured ISIS incorrectly, so that in your real network you would not get an adjacency established, you will not notice it with this. And the reason is, of course, simple, because NetSim only simulates that northbound API. It doesn't actually have an ISIS daemon, so you will never be able to establish an ISIS adjacency. So we really need to kind of do better. We won't be using the force, but we will be using routers instead. Most of our networks still run on physical routers, and we could just go out and buy a few, but costly as they are, we're often much better off with their virtual counterparts. So with virtual routers, we can push real configuration to these virtual routers. And if you look at most vendors, they do provide some form of equivalent to their physical routers as a kind of a virtual router. You have XRV, Juniper has VMX, Nokia has VSR, and so on and so forth. We could, in our testing, we could use physical routers as well, but you got to take care of certain things like resetting the routers after a test run. And if you don't have a lot of cache, you probably can't simulate a very large, complex topology. You're probably limited in what you can test. Or you can't do many varied tests in parallel, kind of. So you're limited that way. I guess as a side note here, we're actually doing, or we want to do some tests on physical routers, but right now we're doing most of our tests on virtual ones. And of course, so the virtual routers are the contrary to physical ones, right? They're very cheap to spin up. We just need CPU and a lot of RAM, and we can kind of simulate a very complex topology or run many tests concurrently if that's what we want. I just made a kind of quick list here of a lot of the virtual routers that are available. I just spent an hour Googling, and this is kind of what I came up with. So there's a lot of it out there. What you usually get from the vendor is some form of image file, an ISO, QCOW2, VMDK, whatever, something like this. Then there's a bunch of different ways to start this up. You have different types of interfaces, like VirtIO NICs. It could be emulated E1000s. Some of the virtual router wants special CPU instructions. And I think pretty much all of them have different ways of providing an initial configuration to this virtual router. So while it's great and convenient in one perspective, actually managing a lot of virtual routers can be cumbersome and quite manual in nature. And this is why we have VRNet Lab. So VRNet Lab is a project. I started writing on this a couple of months ago. It's using Docker and KVM. So we package up a virtual router inside of a Docker container. We're still using KVM emulation, just like we used to. So in fact, Docker here is mostly used as a way to yield a very simple interface. We ship this as a single unit. I don't know if you work with like VirSH or something to manage KVM virtual machines. You know that you have an image file, a configuration file. If you want to have some form of launch script to configure your virtual machine, that's another thing. It's a lot of files to ship around. So with Docker, we can just package all of that up into one Docker image, and we ship it as a single unit. We can also reuse all the Docker infrastructure, Docker registries, so forth, to get this kind of moved around in our environment. The VRNet Lab comes with a bootstrap, or it has a launch script in there, right? That takes care of basic bootstrapping, doing things like creating a user for us. It sets up SSH, netconf, obviously. It also gives each virtual router an IP address. So all of these things combined, it just spins up a machine that we can use in our testing environment. It also has very flexible networking. I'll talk about that in a moment. But above all, it's very simple to use. So this command that you see there, that's all you need to do to start up a virtual XR router. And this is exactly what the command looks like in our CI environment when we want to start up virtual routers. VRNet Lab is free and open source. Just Google it. So just kind of expanding a little bit on how it looks inside. This is the VRNet Lab diagram, kind of how a Juniper VMX looks like. The VMX is one of these virtual routers that consists of two virtual machines. One is the virtual control plane, and the other one is the virtual forwarding plane. Both of these run inside the container. We have a launch script that takes care of starting these things up. And doing some, that initial configuration that I was talking about. It's also kind of monitoring them and making sure that they're actually running. So sometimes it happens that the virtual forwarding plane doesn't really boot up correctly, and it will restart it. There's Linux bridge connecting these two together. And here's one of the things, right, with containers, because you get namespaces. So it's called the same brint in all of these containers, but since they're different namespaces, we don't need to think about naming collisions. SSH and SSH of the virtual router is exposed outside. So it's available on TCP port 22. The serial console of the virtual control plane is mapped to port 5000. This line is actually wrong. The virtual forwarding plane serial console is mapped to 5001. And then we have a little bit of a funny design, as all the emulated NICs of the virtual forwarding plane, they're exposed outside of QEMU as TCP ports. So when we want to connect two of these virtual routers together, what we actually do is we open up two TCP connections like this to the first virtual router, and then the second one like this to the second virtual router. And then we just connect the data together, like a pipe or something. And then the question is, why are we doing this, right? Why aren't we doing it in a more, normal way? So the nice thing about this is that we can start up all the virtual routers without knowing the topology that we want. We just start them up, and then we define the topology essentially through the configuration of VRXCon. VRXCon is also part of the VRNet Lab, so you just get this whole thing on Git, and that's it. So this makes it easy. We can change the topology if that's what we want. If we want to simulate a link failure, we just tell VRXCon to remove a link. If we just want to change the topology in overall, we can do that as well, right? And I think it's good because the virtual routers take some time to actually spin up. take a couple of minutes to start. So this makes it much easier to change things rapidly. A very important aspect, I think, of using VRNetLab is that it allows you to keep the configuration of VRNetLab in your Git repository. So if you have different developers or you want to test things in parallel, you have many ideas, then just as normal with Git, you have many different feature branches or something like this, and you can just change the configuration on this little branch that tells you VRNet topology should look like this, right? Or it should look like this. So if there are many developers, you want to change the configuration, no problem. And this, it might seem trivial, but I think it's really important actually when you're doing CI testing. Previous to VRNetLab, we had a different system, and the configuration resided outside of the Git repository, which meant that when you were doing changes, you had to do this kind of in a lockstep fashion, where you change that system was called Netlab, the Netlab configuration, and then change the Git. This is the pipeline in our CI system. So this is actually a screenshot from GitLab CI. We're using GitLab CI. You can see we have 5 different stages. They're called build and prep, test, Docker push, deploy, and finally clean up. We start over here, the build and prep. The build is what's doing a lot of, it compiles everything, and the output of this stage right here is actually that Docker image that I was talking about. So we compile, we build the Docker image. We do actually run some unit tests in here as well. We do have those. The other part here is, as a prep stage, is a little bit of cheating, because over here in the test, we want the virtual routers, but they take some time to start up. So we actually cheat and start them over here, but disregard that. There are 2 tests. There's a test BGP, and that's the CI for BGP routing policies that I will kind of come to at the end. Then the other one is the one called test topo. And this sets up a topology. I think I have it here. Yeah, it's this one. Okay, well, I'll talk about that in a minute. So it sets up a kind of a large topology and then run various tests on this to check ISIs, kind of on our backbone links. We check IBGP things. Well, just check a lot of different things. So if the test completes successfully, like they've done here, we can see a little green thing. We move over to the next thing, which is Docker push. At this point, we already had the Docker image, right? We tested the Docker image, and what we're doing here is we're uploading this Docker image to our registry. So now it's kind of available for deployment if that's what we want to do. And that's where the next stage comes in. So what we have here, we have 3 different builds. One is called deploy 276, and so this is actually deploy into the region called 276. And for those who know your ISO 3166-1 country codes, that's Germany. So this is to deploy into the German pilot. Yeah, it's not run automatically. You have to press that little button, but we'll get there one day, I think. Okay, so here's the topology that we set up. We currently do 3 different vendors, right? Alu is these days Nokia. So we have that, we have Juniper, and we have Cisco. And as you can see by this thing, we kind of, the R2 here, that's our core router, and we have the R1s as circles out here, the edge. And through this topology, we get all the various permutations of different links. So we want to test the Cisco R1 to Cisco R2, that's here, or there. Cisco R1 to Juniper, this one, or to Nokia, this one, right? And it goes around for all of them. Okay, so at this point, we have a CI environment. We have the provisioning system, NCS, packaged into a Docker container that we can spin up in the CI environment, and we have a bunch of virtual routers connected in this topology that I just showed. Now, what do we test? What do we actually, what do we do with this? What do we test with? So this is where I'd like to introduce the concept of what I call service line monitoring. And I'll show here over the next couple of slides what it is and how it works, kind of. First, a word on what to test with. This is really simple. I think use real-life data when you can, and when you can't, then you are allowed to kind of fall back to artificial data. So only do that when you must. And I'll explain this further, but I'd like, remember this, right? Also like to mention here, unit tests. We do have unit tests, but this is I've seen this a lot, right? People write unit tests, the unit tests pass, and then you ship, and then you notice that things are failing, right? And this is a pretty good display of that. I think the aerospace industry is probably kind of the only industry likely that have the cash really to write the amount of unit tests that you need to actually get a decent coverage. For the rest of us, that mostly out of the question, kind of. So my tip here is to use end-to-end system tests, kind of. What we do is you try to cover more of a system rather than looking at individual functions or units that you test the whole thing. And obviously, this is much, much cheaper to implement, costs a lot less development time. But the obvious downside is that any error that you get back from one of these tests is going to be a lot less detailed. So it might just say fail, and you don't know why it failed. I mean, if that happens and you do want to find out, well, you can always complement it with a specific unit test for that, right? But yeah, end-to-end testing more. I think that's where we start out. If you remember from one of the first slides that I showed just after the stack of pancakes, all these different layers, or the high-level intent, is something that we call a service. So the APIs between all these systems are working with services. So you have low-level services and you have high-level services, and the in-between is kind of where you enrich these and add more data. And it typically falls down the stack when you're ordering something. Everything in our network is a service. So you want a residential customer, that's a service. You want a backbone link, service. You want eBGP to a peering partner, service again. So just all the various things that might shoot down configuration to a router is modeled as a service. This service is kind of it's an abstraction layer, right? And I think that we should think about monitoring in the same way. If you look today, all the networks, or most networks, including our, we do a lot of monitoring already. And the issue is usually that there's a kind of a disconnect between what is provisioned and what we monitor. So service-aligned monitoring is all about putting the monitored data in the context of a service. So the customer of a service, that is, the party that ordered this particular service, and this doesn't actually need to be an end customer, right? This could just be another internal system that we have. That customer should not need to know all the intricate details about the service. This is why we have the abstraction in the first place. They should just be able to order this high-level thing. And since all of the services are essentially abstractions of more complex configuration, the monitoring needs to align with this. And I'll do a dumb example of this. So we have a customer that goes, hello, I would like to order service foo. Up until our RTNSM system replies, okay, I fix, here's your service. Next up, the customer, and this is in the mismatch scenario, right? This customer goes, is service foo working? Up until the system replies, I don't know, but you can ask me about ARP or BGP. Customer, slightly frustrated at this point, what the bleep am I supposed to do with that? I don't know anything about the details of this service. So this is not what we want, but this is what I've seen a lot of in, well, most networks really. the line version. It's pretty simple, right? This time, customer goes, is service foo working? Up until our system replies, yes. Here's an example of where I show this on one of our services. The service here is, so this is in Yang, it's kind of under the category of infrastructure. Service is called backbone interface. This is the router, that is the interface. I think we have, right. This is what we're running, the request. So we're asking for the action self-test on this service. What we're actually looking here, this is the CLI of NCS, but all of this is also available northbound from this system to the other systems and over a netconf or restconf API. So you ask for a self-test, what you get back, you have the main return code. This is very simple, it's a single leaf called success, it's either true or false. But you also get this whole blob down here. This is actually just one big text message that we're currently using. I think I did this mostly for development purposes. If we want, we can return much more structured data as well. So one of the nice thing here is, right, I mean, I'm showing an example for a backbone interface. But regardless of which service we're looking at, some of the result is always the same, namely this. Success leaf. So I don't even know, or I don't even need to know which service I'm asking, this self-test for. All of them returns that success message. So the monitoring system can just ask, are you working, are you working, are you working? And they'll reply to that. Right, so not only do I not need to think about what service I'm asking about, I don't need to think about what vendor this is implemented on, right? So in the last slide, the R21 was an ISXR router. This is a this is a Nokia router, and we're getting back kind of the same thing. This is an old screenshot. PIM neighbor is implemented. Okay, so here's, I'm not sure if you can see this in the back, but this is just a screenshot I did of one of the other services. This one is called DWDM interface. Again, we're asking for a self-test. This is saying, yeah, it's working. The difference here is that we're getting a lot of data back, right? And all of this is structured. So you don't really see that here, but it is. So if you ask over netconf, it would be very apparent what it actually is. So this data is something that we can then feed back into the optical control plane that we have that figures out what the output power of all the optical links should be. You also get lots of other OTN blah, blah, blah stuff there, if that's what you want. So to kind of sum up this part, and I guess for the real price, what I describe here as service line monitoring is really kind of a tool for monitoring of a real network, of a production network, right? What we're doing is using this tool that's meant to be run in a production environment. We're also using it in our CI environment to test that our provisioning code is doing the right thing. One of the previous example, if we haven't configured ISIS level 2, the adjacency wouldn't come up. With this, we have virtual routers. If we configure something incorrectly, it won't come up. And the self-test will fail for that service. So we're getting kind of, two things for the price of one use. So yeah, kind of think of this as, doing the same abstraction for your monitoring as you're doing for your provisioning configuration part. When you're doing service line monitoring like this, I think it's also pretty evident what parts you actually need to monitor to make sure that your services are working correctly. It kind of folds in naturally. You configured it, you kind of monitor the same thing. Right. And the common response there, I kind of commented on that already, that we have a part of the result code is always common, so we know if a service is working or not. I'll skip over to the next part, which is how to use continuous integration testing for BGP route policies. And this is kind of my latest venture and something I'm very excited about. I think that we're actually first in the world to do this. If anyone is of a different opinion, please correct me. So, testing BGP. How do we test BGP, and in particular, our routing policies? The internet is a pretty vast place. We have north of 500,000 prefixes. There are tens of thousands of IPv6 prefixes. And this means that it can be rather cumbersome to actually use all this data in a test scenario. So this is, and I mean also if you think about your entire network, you might not be doing all of that in your CI environment. So it's not a one-to-one map anyway. This is one of the places where I think it's okay to use artificial data. All the other service monitoring, that's actually using real data from the routers, but in this case, it's just much more easy to use artificial data. But how do we structure the tests? First, we'll just go through kind of a typical BGP environment in a service provider network. So I think most of them follow, at least from a very high level perspective, most of them follow a kind of a common model. You have a couple of different sets of neighbors, typically customers, you have peering partners, you have transit providers, or if you're a tier 1, you might not have anyone in that category. Then we have a high-level routing policy that guides what is announced to where, right? It might look like this. This is what I will be using in the examples here, but I think it aligns pretty well with what most people are actually doing. So we announce our own aggregates and customers to peers and to transit. Hello? Oh. We announce our own aggregates, routes from customers, peers, and transit to our customers, right? And then there's an IBGP full mesh, typically between your routers. Maybe you do route reflection. Doesn't really matter. You can also, go full fancy on that, setting metrics or do limited route propagation or whatever. But anyway, think about this one. This is what we'll be using in the examples here. And it might look something like this, right? Lots of different colors, lots of things. Looks a little complex and hairy. But as always, with computers, divide and conquer, we look at it in smaller portions, and that's how we solve it. So if we look at transit, we'll see routes from transit are propagated over IBGP and announced to customers. Routes from transit are not announced to other transit or to peers. I guess the diagram is actually wrong there. Disregard those green ones. Okay, so peers, similar. Routes from peers are propagated over IBGP and announced to our customers, but routes from peers are not announced to other peers or announced to transit. Customer being the notable exception, kind of, because routes from customers are announced everywhere, unless they're under some form of PA prefix, in case we just aggregate them and announce the aggregate instead. Everyone is familiar with this whole concept. Yeah, okay, a few nods, good. We can complicate it further by adding control communities. Don't announce to peer, blah, or prepend to someone else, or do black holing or whatever. But it's really, from a testing perspective, we just do the same thing. Just add more tests. We can test one thing at a time if that's what we need to do. But how do we actually structure it, right? How do we do the test? And to facilitate this, I've written something called VRBGP. Again, this is part of VRNet Lab, packaged in Docker. Surprise, surprise. It's a little Python script that starts this entire thing. That launches ExaBGP, which is used as the actual BGP speaker here. Then there's a little simple HTTP REST API that has 3 endpoints. You can ask about /neighbors to see the status of the configured neighbors. You have /announs, which is you feed it a JSON data blob, and this is what it will start announcing. And you have a /received, which is the vice versa kind of that. You ask it for that, you get back a JSON blob about what routes it has received. So if we look at this over here on the right, the router on the test is the one in the middle, and transit, peer 1, peer 2, customer, blah, 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 all these, they are simulated by VRBGP. What we actually do in our CI environment, so CI is running inside of a Docker container, starting up this little test orchestrator that is then starting the VRBGP instances. It's making sure that the virtual router is running. It connects these things in the topology that we want. And after that, it fires off the actual test script. So the test script is what kind of implements the logic of what we should test. Yeah. So just to be clear here, right? What it does is tell all of these different VRBGP speakers to inject various routes in here. And some of them might have control communities, some of them might not, but it injects a lot of them. What we're doing next is collecting the received routes from these different BGP speakers, and then we're doing our whatever test verification test verification we want to have done on that. So the actual test script is implemented using the unit test library in Python. There's a couple of convenience wrapper functions. You can see it right in here. So this collects the received route from the speaker called BGP peer 1. If we just go back, you can see it's that one, right? Actually, so before all of this, you have some piece of code that tells you, announce the correct prefixes, right? The test prefixes. So after we fetch these received prefixes, we're storing them in a little variable. Then we're using all the normal unit test functions. The assertions, we assert not in this one. So this prefix comes from peer 2. This prefix comes from transit 1. This one from transit 2. We make sure that none of these are in the routes that we received. And thus we know that our routing policy on the device is doing the right thing. And down here, this is where we actually see this thing working. And it succeeds. So one of the very nice things about this is that the protocol between here is BGP, and that's the standard. So we don't need to look much of anything at what's going on under the hood here, because we're just interested in the information passed over these BGP sessions, right? So we can swap out this router. If it's a Cisco router, we'll put a Juniper router instead, or a Nokia router, or something else, and all the tests can remain the same. And we can still run the very same tests on it, and make sure that all of the router platforms that we have behave the same way when it comes to the BGP route policies. And if you've ever kind of maintained complex policies using control communities and so forth across a couple of different vendors, I mean, it's complex on one vendor. Doing it across 4, like we're trying to do, is complex. So this is an immense help in that. So I would like to kind of conclude with the following. So with rigorous testing comes confident deployment. I think that having a good CI setup can be very liberating when you're developing. When you're writing your code or configuration template, the CI system and all the tests that you have, that's your safety net, right? Investing some time in doing this it definitely pays off. It's rewarding. I realize I've not gone into a kind of great detail. I don't think that time would allow for that. But I do hope that I've kind of given some inspiration on how to set up a CI environment and how you can structure your tests. All right, thank you.